What's up, my stat stars? In this video, we're going to talk about some top questions that I'm 95% confident you're going to see on this year's AP Statistics exam. Now, as much as I wish I could say I had some elaborate heist and break into the College Board headquarters where I stole the questions so I can give them to you, well, that didn't happen. But what I am good at, really good at, is probability. And I do know what the past 10, 20 years of AP Stats tests have looked like, and I know that these questions are typically on the exam in some shape, some format. These concepts are going to come up. So if you can understand these concepts and be really good at them, it's a couple questions that you know you're going to get right. Let's take a look at them now. In this first question, Doug has a large batch of apples, thousands and thousands of apples, and he wants to estimate what proportion of them have wormholes. And he wants to do so within plus or minus 3%, that's his margin of error. And he wants to do so with a 98% confidence interval. So here's the question, what's the minimum sample size he needs to achieve this goal? Again, to have this margin of error of plus or minus 3%. This type of question comes up on the AP exam every single year where you're solving for the sample size. Let's take a look at how to do it right now. So to answer a question like this, we first have to understand the formula for the margin of error. Now, when you're constructing a confidence interval, the margin of error is the back part that you're adding and subtracting. Now, when we're working with a single sample proportion, here is the formula for margin of error. The margin of error is that critical Z star times the standard error formula. Now, for standard error for proportions is giant square root p hat times 1 minus p hat divided by n. Now, all we have to do is fill in everything that we know. The first thing we know is the margin of error that Doug wants to achieve is 0.03. The next thing we need is the the Z star for our level of confidence, which is 98%. Now to get that, I'm going to do invert norm on my TI-84 calculator, and I'm going to look at the 98% in the middle, so I could do 98% center, or I could look at the 1% to the left, and that's going to give me the Z star that I need here, which is of course 2.326. Not overly difficult. Now, the next thing is, what do I do for p hat? Because I don't even have a p hat. I don't even have a sample yet. So that's where we just use 0.5 and 0.5. If you have no idea what to do with p hat, just 0.5. It's that simple. Now we begin the algebra portion. The first thing we're going to do is divide over by the 3.26. And we have to then square both sides to get rid of that square root. Then we're going to take that n in the denominator and multiply it over to the left-hand side. And then we're going to take this entire value, the 0.03, divided by 2.326 squared, and divide it over to get our final sample size m. And in this case, we get roughly 1,503 people. Anything less, and I'm not going to get that 3% margin of error, and anything more, I'm going to actually have a lower margin of error, which would be even better. In this question, we're looking at a two-way table, and we see that a large group of students at a university were asked two questions. Do they come from a suburban, rural, or rural hometown? And what is their college major? Now, a question like this, we're going to see this. If there is no association, which means independence, how many students should be from a suburban community and taking engineering classes? Now, this type of question comes up every single year. It's related to a possible chi-square test or just examining a two-way table looking for an independence. But what they want to know is how many kids we should see in one particular cell if there is no association. Let's talk about how to do it right now. Now, when you're working with one of these problems, the first thing we want to do is identify the cell that we're talking about. Engineering and suburban right there. Now, what we want to do is figure out what's the expected number that's supposed to be in that cell if there is no association. And it's the easiest formula ever. All we got to do is take our row total times the column total divided by the grand total. It's that simple, and that's true to find the expected value in any cell. Row total times column total divided by grand total. So I'm going to take 542 times 216 divided by 1,000. Now, sometimes the questions leave it in that format. Other times they actually have you go ahead and, kind of force you to do the math. And obviously it's nothing difficult. Just grab a calculator and we should get 117.072 people in that cell if there was no association. It's really that easy. Just remember row total times column total divided by grand total to get your expected values in any two-way table. This next question is also very, very common. It deals with two different random variables and combining them, looking at the sum or looking at the difference. Now, in this particular question, we're looking at two different kids and they both play the same video game and their scores are independent of each other. We know the mean and standard deviation for each of them and we want to know what's the probability that one does better than the other. Now, this question is very, very common because we need to know how to combine random variables to find the mean and standard deviation of the difference, and then use those values to calculate a probability. Let's dive into it right now. So the number of points Vance scores in a random game follows a normal distribution with the mean of 152 points, a standard deviation of 18, and the number of points Steve scores in a random game follows a normal distribution of 140 points, a standard deviation of 25. Now, there's all different kinds of questions that can be asked here, but the two most popular are talking about the total or the sum of their scores or the difference of their scores. And this one's going to focus on the difference, and that's usually more difficult. Now, here's the question. If they each play a random game, what is the probability that Steve will score more points than Vance? All right, so here's how we notate that. We're trying to find the probability that Steve is greater than Vance. Now, if I subtract the V over, we're trying to find the probability that Steve minus Vance, the difference between Steve and Vance, is greater than 0. Now, they both follow the normal distribution. So looking at the difference of their scores is also going to follow normal distribution. So all we have to do is build a distribution for the difference, Steve minus Vance, and locate 0 on that model, and then look at the area above it because we want that difference to be greater than 0. Now, building that standard or building that model is first. So first we have to find the mean of the difference. Well, Steve 140, Vance 152, that's a difference of negative 12, Steve minus Vance. That means Steve is supposed to do 12 points worse than Vance. But they both deviate, so maybe Steve does better, Vance does worse, and all of a sudden Steve is higher. So what's the standard deviation for the difference? Well, this is where we have to remember a couple simple rules. First, we cannot combine standard deviations. We have to first combine their variance. Now, to find variance, all you got to do is take Steve's standard deviation and square it. Take Vance's standard deviation and square it. Boom, now we have the variances. Now we're going to add that variance together. Now, wait a minute. We're looking at difference. Why are we adding? Well, no matter what, looking at the sum or the difference between two random variables, the standard deviation and the variance, it always builds no matter what. So I'm always going to add. Another key rule when it comes to combining standard deviations. Then I need a giant square root around all of that combined variance to get back to a standard deviation. So my combined standard deviation for the difference between Steve minus Vance is 30.806. So now again, I can imagine this model. I'm going to just draw a really rough picture. And I told you it was normal. Right smack dab in the middle is negative 12. There's supposed to be a negative 12 difference between Steve and Vance. And then we could go up 1, 2, 3. We can go down 1, 2, 3 standard deviations. And if we go up enough, we're going to hit a positive value. And a positive value means Steve did better. Because if I'm doing Steve minus Vance and I get a positive number, that means that the S was bigger than the V. And that's what we're trying to find the probability of. So all we have to do is locate 0 on this model. And that's, of course, why we need a Z-score. So the Z-score for 0, why am I investigating 0 again? Because I'm trying to find the probability that the difference, Steve minus Vance, is greater than 0. Because if it's greater than 0, then Steve did better. It's a positive number. Come on. So we're going to take 0 minus the mean that we just got of negative 12, divided by the standard deviation that we just got of 30.806. And that gives us a Z-score of 0.3895. So if I go back to this terrible normal model picture I just made, we're looking at a Z-score right around here for 0. And anything above this is going to be where we get S minus V to be greater than 0, which means Steve did better. So then all we got to do is go to normal CDF on our calculator and find the probability that a Z-score is greater than 0.3895. Hopefully you already know how to do that. Very simple to find the probability that a Z-score is greater than 0.3895, just using normal CDF. And we get 0.348. So there's a 34.8% chance that in any random game, Steve is going to score more points than Vance. Not too bad, but definitely one of the more difficult problems just because it has a lot of steps to it. In this next question, you're going to be given a situation and you have to identify what sampling technique was used. Stratify, cluster, systematic, or simple random. There's usually a fifth choice like convenience or volunteer to throw you off. Now, this type of question comes up almost every single year on the AP exam. So here's a quick example. At Dana's college, there are 10 college majors, and she wants to get some information from the students about graduation. Maybe things they prefer, things they like, or the things they dislike. But she doesn't have time to measure everybody, so what she does is she gets 5% of students from every single major chosen randomly to be in her sample. What type of sampling technique is this? Well, because she visited every single college major and took some from each, so she essentially separated her college into groups. Groups are based on majors, and then she took some from each, 5%, keeping it a nice proportional value. That's going to be a stratified random sample because she took some from each group. Now, if she only selected 3 college majors in total randomly and used all of the students in those majors, that would be a cluster sample, but that's not what she did. Plus, she wants equal representation from every single major. Now, simple random sample, the majors wouldn't even matter, and we would just have a big list of all the students, and she'd just take 1,000 of them off that list at random. But make sure you're prepared for this question by knowing the different sampling techniques, because it's bound to come up. In this next problem, you're going to be shown a probability distribution for a discrete random variable, and you're going to be asked to calculate the expected value or the mean for the random variable. This problem is really, really easy to do as long as you know how to calculate an expected value with a probability distribution. All you have to do is take each outcome, multiply it by its probability, and add them all together. Let's look at an example right now. The manager of a large wholesale warehouse store tracked the number of rotisserie chickens customers purchased for 3 months. The probability distribution of the number of rotisserie chickens purchased at each transaction is below. So here we see a discrete random variable with outcomes of 0 chickens, 1 chicken, 2, 3, 4, or 5, and the probabilities below. All those probabilities better add up to 1 or you did something wrong. Now, what is the expected value for the number of rotisserie chickens purchased per customer? Well, that's the same thing as asking what the mean of this discrete random variable is. And again, all you have to do is take each outcome, multiply it by its probability. So here's my work for how simple that is. 0 times 0.15 plus 1 times 0.4 plus 2 times 0.35 plus 3 times 0.05 plus 4 times 0.03 plus 5 times 0.02. Very simple math, quick and easy on your calculator, and you get an expected value or a mean of 1.47. Now, what this means is in the long run, after looking at many customers, on average, each customer buys 1.47 rotisserie chickens at this particular place. In this next example, which comes up, again, almost every single year, is how do you construct a confidence interval for the slope of a regression line? Now, in a multiple choice question like this, you're going to be given a regression computer output that has everything you need in it. But all you need are 2 things from the table. First, the slope of the sample, and the standard error of that slope. Now, those 2 numbers are exactly next to each other in the table, so they're really, really easy to find. Now, the only other thing you're going to need to know is your t-star, which is based on how confident you are, which will be said in the problem, whether it's 90, 95, 98% confident. Now, the one thing that tricks students up the most on this type of problem is the degrees of freedom, because to get that t-star, you need your degrees of freedom. Now, with slope, remember, degrees of freedom is your sample size minus 2. Now, as long as you remember that, you can calculate your t-star, and it's really, really simple to build that confidence interval. Let's take a look at an example right now. In this example, we're looking at a windmill, and for each of 25 randomly selected days, we measured the wind velocity in miles per hour and the electricity production in amps for that windmill. Now, that's going to produce a scatter plot where we see a bunch of dots, and each dot represents the wind velocity and the amps for that particular day. And then we're going to see a relationship there. Now, the slope that we see in that scatter plot is just the slope for those 25 days, but what about for the population of all days? Well, that's exactly why we could construct a 95% confidence interval for the slope for all days. Now, again, as I mentioned, all we need are just a couple things. First, we have to remember that this very first column is the A and the B value. A is the y-intercept and B is the slope. We're not using y-intercept, we're trying to find a confidence interval for the slope. And then the other thing that you're going to need is the standard error of the slope, which is right next to it, 0.019. Everything you need is right there in the table. So all we got to remember there is how to find the generic formula for a confidence interval. We're going to first start off with the sample statistic. In this case, that's our sample slope B, which is 0.240. Then we're going to go up and down by a critical value times our standard error. And like I said, that standard error was literally right next to that sample statistic or that sample slope. And that standard error was 0.019. The only thing we're going to have to go and calculate is that critical value. So here's how I'm going to do that. First, I'm going to go to invert T on my calculator to get a t-star. And we ask for a 95% confidence interval. That's going to put 0.025 at the bottom, 95 in the middle, 2.5% at the bottom. And then the degrees of freedom. Well, remember, sample size minus 2. So 25 days minus 2, 23 is my degrees of freedom. This is going to get me that T-star I need, which is probably the one thing that kids mess up most that prevents them from getting the right answer. So 2.069. All right, now all I got to do is multiply the margin of error, multiply the critical value times the standard error to get the margin of error, and I get 0.240 plus or minus 0.0393. Now, sometimes you'll see choices that actually look like this, where they keep it all separated. Sometimes you'll see choices that look like this, where the margin of error is calculated, and sometimes they might actually go ahead and construct the interval, adding and subtracting that margin of error. And in that case, we get 0.2007 and 0.2793. Now, I've also seen problems where the answer is the explanation for the confidence interval. Now, remember, this is a confidence interval for the slope. And here we're looking at, for each increase of 1 mile per hour, what we expect the electricity production to go up by in amps. So we're 95% confident that for each additional 1 mile of wind, we're either going to get somewhere between 0.20 more amps of electricity to 0.28, I did a little bit of rounding there, more amps of electricity. And again, that's exactly what the confidence interval is going to do. But make sure you know how to construct this confidence interval because it comes up every single year on the AP Statistics exam. In this next type of question, you're going to be asked to describe a sampling distribution for a p-hat, a sample proportion, or an x-bar sample mean based on a certain sample size. Now, this question's on the exam every single year. It's maybe not going to cover both means and proportion. There's definitely going to be one of them. Now, if it's a proportion-based question, you need to be given two things. First, the population proportion P and the sample size N. And then what you could do is you could use the formulas to actually construct the mean and the standard deviation of the sampling distribution. But you also have to check that your samples are big enough, that way you could be normal. And if you want to be approximately normal, with proportion, you need to have 10 or more successes and 10 or more failures in all of your samples. Now, if it's a problem dealing with means, you have to be given three things: the population mean, the population standard deviation, and your sample size. And then you can use the formulas to find the mean and standard deviation of the sampling distribution. But you also have to make sure that you're approximately normal. And for that, we have to make sure that our sample sizes are 30 or more. So the central limit theorem tells us that the sampling distribution will be approximately normal. Let's take a look at two specific problems right now for proportions and one for means. This first example says, according to an environmental website, 35% recycle plastic water bottles after use. For random samples of size 50, describe the sampling distribution of p-hat, the sample proportion of 50 people who recycle their plastic water bottles after use. All right, so this is really easy. So there's formulas for this that are so simple. All you got to do is look at the back of your formula sheet and go to the part for proportions. And we're obviously dealing with one sample at a time here, but we're going to build a sampling distribution that shows all possible results for p-hat. Now, this is really, really simple. First is the center, the mean of all those p-hats, and that should always match the population proportion, which is 0.35. Now, this is only going to be true if our samples are random, as long as we avoid bias, and of course it says that. Next up comes the spread, or the standard deviation, because guess what? All of those p-hats are going to deviate. They're not all going to be 35%. So here we have a very simple formula as well. It's the square root of P, 0.35, times 1 minus P, which would be 0.65, all divided by your sample size. And the reason why we got divided by our sample size is because bigger samples vary less. So don't be afraid to grab a calculator to do that math. It's fairly simple, not overly difficult, but we get 0.0675. Now, the only way that this is going to work, the only way that this standard deviation is going to be accurate or usable is if our sample size is less than 50 or less than 10% of the population, so we could assume independence, especially because we don't know if we're sampling with replacement or not. But we can assume if we're talking about all people, even if we just say people in the United States, we assume that these random samples of 50 are definitely under 10% of the population. Now, we got the center, we got the spread. The next thing we need is the shape, and of course we want the shape to be normal, or at least approximately normal, but the only way we can guarantee that is if we have 10 or more successes or 10 or more failures in our sample. So if we have those 50 people in a sample and 35% are supposed to recycle their plastic water bottles, we get 17.5 successes. That's definitely more than 10. And then we also need the 65%, that's our failures, the people that don't recycle, to also be 10 or more, and that's 32.5. So since both of those numbers are 10 or more, our sampling distribution could be normal. If this right here failed, then we would not be normal. We could still have a center, we could still have a standard deviation, but we just wouldn't know for sure that our sampling distribution was normal. And that could come up on the AP exam. But questions like this come up every single year. Now, if you don't see more than one one for proportions, you're probably going to see one for means like this. The mean weight of tarantula spiders are 57 grams with a standard deviation of 19 grams. For random samples of size 40, describe the sampling distribution for X bar, the sample mean weight of the 40 tarantula spiders. All right, so let's dive into this one. First, what is the center? What is the mean of all possible sample means of 40 tarantula spiders? Well, that should match up with the population mean of 57 grams. That's pretty simple. What about the standard deviation? Because all of those sample means are not going to be 57. Some are going to be higher and some are going to be lower. So this is where we take the population standard deviation of 19 and divide by the square root of our sample size. Now, the only way that's going to work, or the only way we're going to be allowed to do that, is if we could assume independence and without sampling without replacement or with replacement, we just don't know. That's why we have to make sure that 40 tarantula spiders is under 10% of the population, and I could definitely assume that to be true. So there's the standard deviation of my sampling distribution. And lastly, the shape, well, we want that shape to once again be approximately normal. Now, that's only going to be true if our sample size is 30 or more, or if the population is known to be normal. Now, it never said the population is known to be normal. In fact, a lot of times on the AP exam, they'll actually tell you that the population is skewed left or skewed right to try to throw you off. But as long as your sample size is 30 or larger, the sampling distribution is going to be approximately normal according to the central limit theorem. And since our sample size of 40 is definitely more than 30, we're going to be approximately normal. So there's the center, there's the spread, and there's the shape. Again, questions like these come up all the time, so be prepared for them. And those are the questions that I think are going to be on this year's AP Statistics exam. Now, I could be wrong, and you know what? That's okay. But trust me, these concepts are going to come up, whether it be on a multiple choice or an FRQ. So just listening and paying attention, understanding them is going to actually help you score better on the exam.